For the second lecture on linear kinetics, we're going to talk about different types of forces that we identify in human movement and how we interact with our environment. Now, I want to take the time to say that this is not all inclusive of forces. I'm taking the liberty of choosing some forces that I think that are really pertinent to some concepts that we're going to talk about in class and how to describe general human motion. But there are a number of other forces out there that we are not going to touch on. So just understand that this is not an all-inclusive aspect of types of forces, but more some of the ones that I think are relevant for the discussion here. So what it really needs to understand is there's going to be two types of forces we talk about. There'll be non-contact and contact. And really the only non-contact force that we are going to talk about is that of gravity. And it stems from the Newton's law of gravitation, in which states that the force of gravity is going to be inversely proportional to the square of the distance between the two objects. So this is an action of two objects and proportional to the products of their masses. So the objects have some distance between them and they each have their individual masses. So this is a very classic equation, and it's truly oriented originally derived from understanding how planets and stars orbit around and how they interact with each other, creating that pull throughout the orbits. So when we talk about this force of gravity on the system, on the human body, we're going to look more in depth at this equation. So if we look at this equation, there's a couple components that I want to make sure you understand. And the first one is going to be this large G here. What that is the universal constant for gravity. Now this is a huge, really large number. You can look it up if you want. It's like 6 point something to the negative to the 10 to the negative 11. But it's a huge number, right? But more importantly for our purposes, what these two M's stand for. So there's an M1 and an M2, and we can say either M1 or M2 is the mass of the Earth. Because we are all on the Earth and we have the gravitational pull of the Earth, that is our second mass. When we talk about the gravitational pull on the Earth, that is what we're talking about. And it's about the center of the core. The second M2 is whatever the object is in the Earth's surface. It could be yourself, but it's that secondary object. And as we talked about projectile motion, that secondary object was whatever was a projectile motion. And it behaved and it had a gravitational pull on it. Now the third component here is going to be this R on the very bottom, and that is the radius between the center of mass of the Earth and the Earth's surface. So the core of the Earth and the Earth's surface. And why that is for any object on Earth is because it's such a large radius between the center of the Earth and the Earth's surface that any true addition to that on top is really negligible. So we just use this R here to represent that on Earth. So if we look down here at this W equals ma, weight of mass times acceleration, and we know that this goes further as to seeing mass times gravity, and that's the body weight of the individual. Then what we can say is, how is this derived from this equation? And because we know this is negative 9.81 meters per second squared here on Earth. So what we're going to talk about is this equation here and how that breaks down, because what we've done is they've taken this portion of the equation, because this is truly a constant, because like I said, this R squared on the bottom is truly just the core of the Earth to the Earth's surface. So this becomes that G, which is that 9.81 meters per second at sea level. And we put that negative just to give it a little directionality to it. But so for our purposes in projectile motion, we have a negative 9.81 meters per second. So now we have the mass of whatever the object is times G. And so that brings us down to this equation. And we have what we know as gravity. So this is where it's derived from. Just understand the law of gravitation is that interaction of two masses. And so it's proportional to those two masses with the gravitational constant, and it's inversely proportional to the distance between them two. Now, the second major category of forces that we're going to discuss is contact forces, and one of the major contact forces that we'll really review in this class is going to be the reaction forces. And what is a reaction force? Well, a reaction force is a force that is provided by the surface with which one is interacting with. Now, a common one that we know and we utilize often is going to be a ground reaction force, and we measure this through many different scenarios. In the laboratory, we use a force plate, and typically it has the three orthogonal components. At your house, you probably use a body weight scale, or in the gym, you use a scale. That is also a lower cost, just vertical ground reaction force measure. But these are simply some measures that we use, and a reaction force typically has three components to it. If we do it in the orthogonal, there's a vertical, an anterior, posterior, and a medial lateral. And what I have depicted here are three representative ground reaction forces. And what these are is this is a typical walking ground reaction force and a typical running. Now, because of this right here, we'll say it's a rear foot strike, and we'll talk more about that at a later time. But these are very typical, where you have a walk, you have this trough at the beginning, and at running you have the peak at the same period. So these are identified of mid stance, and you have a drop and then you have a peak, and we'll talk about that in a later time. But if we go forward, a couple components I want you to know is that this VZ vertical is also known as the normal force. And what that is the one that is perpendicular to the interaction surface. So as you can see, it is coming directly perpendicular to 90-degree angle straight out. And then you have two other forces, and those are the anterior, posterior, and medial lateral. And so these are the kind of the components that we'll be talking about. But going forward, in the anterior, posterior, and the medial lateral are what we typically refer to as your shear forces. So you have the normal and the shear forces of these reaction forces. Normal force is that one that is perpendicular to the interacting surfaces, and then the shear force are typically tangential, that go out in right angles at each other. Again, you have, the direction of motion was going from left to right as seen by here, these are the three orthogonal components of the GRF that you would see from a running profile. As we move forward with the contact forces, the next one is a joint reaction force. So again, we're keeping in line with this reaction force concept, but now we're going to go to the internal body. And what you can see with this image here is essentially a joint reaction force. Represents that force, and so as you can see where these originate, it's on the femur. And so the interaction of the lower leg of the tibia is creating this reaction force from the more distal segment onto the more proximal segment in this case. And it creates, so it's that essentially force exerted by that other segment onto a segment through a joint surface. And typically the joint reaction force is a summation of the segments across the joint. And there's a couple components here that we'll discuss and break. And again, you have that normal or compressive force that is typically directed into the joint surface. So as you can see the direction here, the tibia is pushing from the ground through this joint surface, and it continues on that path. So there's your compressive or your normal force. It's the interacting of the two, and it's typically straight up. Now, the other two components are going to be the shear components that we talked about. Now, this graph only shows you the one going down, but think about there's also one either coming directly out of the screen at you or directly into the screen. It's that third orthogonal component of this. And these are typically act across the joint surface. So these are tangential. Now, the summation of the three, or the resultant of the three more correctly, is going to give you that ultimate joint reaction force. And so that is the measure of joint reaction forces, and you can decompose it into the three orthogonal components. You have the normal or compressive force, and then you have the two shear forces that translates that tibia through the knee joint anterior posterior or medial lateral, more that varus valgus. And this is what the MCL ACL concept is about. as well as some of the other ligaments of the knee, is kind of help stabilize those shear forces throughout the process. As we further dive into the contact forces, we want to identify one that is very important for human locomotion because it provides the basis for the translation or the control of the center of mass during locomotion, and that is that of friction. And friction is a force that acts parallel to the interface, so the two surfaces of two different objects. And that could be in motion or they could be in a impending motion. And it's important to understand that friction opposes that motion or an impending motion of the two surfaces. And we'll talk about how that's important to understand. But to measure it in friction is calculated a couple ways, but it's the resultant of two horizontal or shear forces. And that is the anterior, posterior, medial, lateral that we've talked about previously. But it's also proportional to the normal force. Well, what does that mean? Well, the equation of frictional force is this. The frictional force, represented by F sub F, which is the maximal frictional force, is equal to the coefficient of friction, and we'll talk about that in a second, and the nodal force, which is the vertical ground reaction force, as we measure this in a a force plate in 3 components. But if we look at that and look at this diagram here, we'll take it and say with this graph, and this is a graph that I just want to show you real quick on a log, and it's a physics-based graph, and I like to do a lot of my stuff with biomechanics and human bodies, so we'll get into that in motion. But quickly saying, this is, you can see this line here, so the impending motion is going left to right. Now the weight of the block is being pushed, so the interacting surface is right in between these two, the block and the table, right? So there is a surface of interest at which the friction will be discussing, right? So it's not when you're pulling the force, so it's not here, it's within those two surfaces, and they're parallel surfaces. And so frictional force, as you can see by the diagram, is going backwards. Because of the motion is going left to right, well, the frictional force is going to go towards the back. So it's opposing the impending motion, right? And so what's happening and what this means right now is maybe the block is moving, maybe it's not. I would say it's not moving only because I know where this comes from, but the frictional force is opposing that pending motion. Now, as we take this concept of friction and we apply it to the human body, and we're going to talk about this idea of walking and running and where friction comes into play. And what I'm going to show you here right now is really, in human locomotion, the force of friction is equal to the anterior posterior ground reaction force. And we'll talk about this in a second, because and an important idea with that though is on level ground. So when the surface is level and not running uphill or downhill, and that's an important distinction. Okay, but as you can look at these graphs, look at the center mass here. The center mass is about here. Same with here. But more importantly, I want you to just look at what you perceive happening with the feet. Okay, so this person contacted the ground, heel foot first, out in front of the body. But as they were coming down, because where the center of mass is down here, producing a torque, and you understand what torque is later, if there was not the frictional force going in the posterior direction, what do you assume would happen with the foot? Well, I would assume it would slip and go this way, creating the fall. Same case here. This way, the foot is pushing on the ground to propel itself forward. Okay, we call that kind of a propulsive force, and you'll see that down below. But in this instance, the frictional force is going this way. And that's because in order for that propulsive force to grab onto the ground and propel you forward, then the frictional force has to create that interaction and that clingingness of the ground between the two surfaces to allow you to push forward. Another example is that you can see this down here on the bottom part, where you have the propulsive force and you have the friction force, right? So the frictional force is helping produce that interaction and cling to the ground to allow you the traction to produce that propulsive force. If there was no friction in these two instances, as the person was propelling themselves forward, the foot would fall, and the individual would just fall to the ground because there would be no traction created between the two surfaces caused by that frictional component. You'll see this a lot with different footwear and why we create different increased traction for some, which is it allows that frictional component and the coefficient of friction to increase. So how does this change when you're running uphill? Well, to go uphill, if you see that the impending motion is coming down, but what we also, the really changes is that now we have a different component. Because if this is a free body diagram of this depiction of the person running uphill. And the ground reaction force is this Fg, force of gravity, coming down. Now that creates the normal force. But if we take that ground reaction force and we create the Fy and the Fz component of this is going to be coming this direction. Okay, and that's because of where the location of the ground of the force of gravity is acting. Okay, so it's causing that person to come down. Now, in order for the person to run up the hill, he would need to create the frictional component that creates the traction between these, and so that is going to go uphill, right? Because the foot is pulling backwards. Let me clear this up a little bit and draw it again. So this foot and the interaction here, the foot is clawing back. And in response, the frictional component needs to be here to go. So in this instance, when you're running uphill, that is going to oppose the motion of the foot, right? The impending motion of the individual is uphill, but the foot impending motion is going back down the hill as it's clawing. So therefore, the frictional component has to be up. So this is where that kind of concept of up and down really kind of relates and draws into this aspect of it. So as we go forward, there's a couple components of friction that are important, and this is that idea of static versus dynamic, or where you're in motion is dynamic and you're not in motion, but you're impending that motion, is more of a static concept. And something that you'll understand on the side here is you have the static friction. Kinetic friction is another term for dynamic friction. But what these are ensuing and what you should see is that there's a linear trend or a linear relationship in static and friction. So whatever your two interaction forces are, when it's static, there will be, as I increase that applied force, the frictional force will increase in a linear component, and that component is the coefficient of friction. Now, at some point, the static friction represented here as F sub S is equal to or less than the coefficient of static and the normal force. Okay. The kinetic friction or dynamic friction is equal to the coefficient of kinetic friction and the normal force. Now, one thing that is true and we need to make sure that you understand and see from this graph is the maximal static friction is greater than the dynamic friction. So dynamic friction, no matter how much you increase the force, it remains the same throughout. So there is only one dynamic friction as you increase the applied force. Now, the maximal static friction is greater than the kinetic friction or dynamic friction. And there's a drop. So at some point, and that point is the instant of motion. So right before motion begins, you reach your maximal static friction. So I wanted to go ahead and talk a little bit more about this and show you another diagram and how this relates. And you have a shoe interacting with the surface and environment. A couple things I want to really quickly talk about is what FGY is, and that's just the normal force. It's often referred to as FGRFZ. So I don't want you to worry about their Y is just the orientation for this textbook. Fw is the force of the body weight of the in. Fs is the static friction, okay, and then Fp is that applied force that is responsible. So as you looked at the previous graph, this was applied force and this was frictional force. And the other thing I want you to see is that you don't have that drastic drop here. It does typically kind of gradually get into the dynamic friction once something gets up to speed. So it's not a huge drastic concept. And then the last thing I want to point out is the static friction max here, which is greater than the dynamic friction as it gradually goes. So what this is depicting here is the interaction between these two surfaces as this person cuts. And this is one of those things where as you increase the traction or the coefficient of friction, how much force can you apply into the surfaces that would allow you to stay static or gain that traction versus slipping or versus motion. So the last component of this I want to talk about is this idea of rotational friction, and it deals with mostly with the cycling wheels. And the idea of what this looks like is important because, again, remember we talk about friction opposing motion. And what we have here is that this individual is going right to left. So the overall system, which is the bike and the rider, goes right to left. But the wheels, in order to do that, rotate this way. So the motion of the wheels is here. So as you can see, the frictional component, which is this back one, goes in the same direction as the overall motion of the system. But it's because it's this interaction of the surface here, which is the wheel and the ground, and it's opposing the rotation of the wheels. So understand that not the system motion, but the impending motion at the contact surface, and that's where rotational friction acts. The other key component of this is rotational friction is going to be less than your static friction. Now it's important also to talk about fluid resistance because it's the interaction between an object and that fluid, which can be an air or a water or a gas or liquid, that it interacts throughout. And these are important because fluids often oppose the motion. And as we look at it, there are two main effects of fluids. And that is they produce a lift component and they produce a drag component. And lift is often an upward force on the object, while the drag force is often in the opposite direction of that forward motion of the opposite. And then you have what we consider the resultant vector of those two forces, and that is the fluid resistance vector. And so you'll find whatever the lift vector is, whatever the drag vector is, and create that triangle, and that will be your resultant vector. Now it's important to understand two really important properties that mostly affect objects in motion, and those are going to be the density or the mass per unit volume of the fluid, as well as the fluid's viscosity or the fluid's resistance to flow. And so what I've done is with this other graph that I've taken from one of our textbooks is depict the motion of the individual is going this, or the object is going that way, where the air is coming back this way. And you can see where you have the lift force and the drag force, and then you have the resistance vector or the fluid resistance vector coming directly back. It's important, what we'll talk about a little bit later is breaking these up in components and where the vector comes into play or versus the individual components come into play. But first I want to take you further through some of the fluid resistance components, and we're going to begin by discussing buoyancy. And buoyancy is a force that is acted when an object is submerged in a fluid, more particularly a liquid, and it causes the fluid or the object to be suspended upwards, and that is a vertical upward motion. And the buoyancy, you can see it with the vector here through the center of mass, and that's where the line of action is. Now, what we talk about with buoyancy force is it's calculated by finding out weight of the fluid that is dispersed or displaced by the object. And it's often done when you're in an environment of, you have some known volume of liquid, you submerge the object, and you measure how much weight of that fluid is displaced. But buoyancy force is measured by the volume of the object multiplied times the specific weight of the fluid, which is this little symbol here. And specific weight of the fluid is the weight for a standard volume of that fluid. So every fluid, like fresh water, has a different specific weight than salt water. And as you get more fluid viscosity and density, then it becomes a different specific weight of that fluid. So you have to know the weight, the specific weight, and then you know the volume of the object, and then you can calculate the buoyancy force. But that magnitude of the force is often what we'll do is because we know the specific weight of the fluid, we'll submerge the object without knowing the volume of the object inside of the fluid and measure the weight of the dispersed fluid. Going into the last discussion for this is we're going to talk about drag. First, I want to describe a little bit of the equation and then what this image depicts, and then we'll just talk about the two types of drag that we'll talk about. And again, it's not an exhaustive discussion on drag forces. There are other components of drag, and there are other aspects of drag. There's also lift we could talk about. We're not going to talk about that. We just use buoyancy as our discussion on lift. But the force of drag is calculated with this equation, and it's 1/2, which is a constant. Then you have the coefficient of drag, and the coefficient of drag is going to depend on the object and as well as the fluid which you're going through. But more importantly, we have this A, which is the area, and more importantly, the cross-sectional or the frontal area of the individual object. So that has to deal with how the object is moving through space, because the cross-sectional area, especially the frontal area of that object, is going to affect it. The next one we have is going to be the rho, or this what looks like a P here, but it's actually a rho, and that is the density of the fluid through which you're interacting. And then you have v squared, which is the velocity of the object moving through the fluid. The next thing I want to talk about is what these lines represent in this graph. And these lines are different layers. They call them streamlines. And they're different layers of the fluid at which the object is traveling through. Some are closer to the object, some are further away from the object. So as the object moves through these layers, each one behaves a little differently, and that's what's depicted, and you can really see that in the back of the objects, and underlying the object here on how they behave differently is very essential to describing the motion. But we're going to talk about two concepts of drag that I want you to focus on, and the one is the friction or surface of the drag. And this one's created by that one streamline that is the closest to and touches the outer boundary of the object. And this is really affected by the smoothness of the object. And so that affects the magnitude. And this affects the reduction of an object's velocity. So as the object's surface is rougher, there is an increase in this magnitude of friction or surface drag because of that roughness, and that slows down the object. Now, this is one where a lot of equipment design, like wetsuits or shaving the skin of a swimmer, comes into play, where you're trying to make that surface, the outer surface, as smooth as possible, which allows that friction or surface drag to be reduced. Another one is pressure or form drag. And this is during events of turbulent flow, which means there's a pressure differential, and we can really see that in B, from the front of the object to the back, and you see all these waves, and that's the turbulent flow in the back. So as this pressure differential between the front and the back of the object increases, then there's an increase in this form drag, which then results in slowing down the velocity or causing it more difficult for you to move forward. If you ever hear somebody in cycling drafting, they're trying to hang out in this turbulent flow because for them it's creating this non-difference between the front and the posterior. So if I put a cyclist right here and he's hanging out behind this, that drafting is within that turbulent flow region behind the object in front of him. So this is also one of the things where cycling helmets and golf ball designs are meant. They're designed to decrease and control where the turbulent flow occurs and therefore affecting their drag. And again, this is also very important to understand that when we talk about that concept, this velocity component comes into play because it's important to understand that once you reach the velocity, then we can talk about whether it's beneficial or not. So great. Now, what do we do with all these forces that we know? And so what it's going to be used for is it's going to be used to create something that is called the equations of motion. And so when we discuss how people move throughout an environment, we use equations of motion to describe that motion. And when I ask you to create the equations of motion, I'm asking for, and I'll talk about what those equations are in a second, but I'm asking you really to create a free body diagram. And the free body diagram is a representation of whatever system I'm talking about. You understand that more in a second. But it's just a stick figure, and all you're doing is creating the vectors and where they are interacting on that system. Now, one key component is this: you're only including external forces. Part of this lecture, we talked about joint reaction forces, and those are internal forces. So all I want to know is external forces, forces of gravity, ground reaction forces, air lift and drag, and buoyancy, and propulsive force, and all those type of things. These are all external forces. So that's very important. Okay, and so what we're going to do is typically when I ask for equation of motion, I'm looking for two equations. I'm looking for the equations of the vertical, which is the sum of the forces. I'll just put Z, or ground reaction in the Z, so it's vertical, equals the mass times the acceleration in the Z. And again, acceleration is just motion. What are these forces doing to the motion in that direction? It could be that this is zero, there's no motion going on right now, right? Or no change in motion. I also want the sum of the forces. I'm going to put AP because sometimes it's X, sometimes it's Y. And in some cases it's even Z, but so force is the AP and mass times acceleration in the AP. So these are the two concepts. Now, what is often going to happen is what I don't want you to do is you're not going to create a value for the right-hand side of the equation unless we know what the motion is. If we know it's a static motion, then it's a zero, and then it equals zero. But for most instances, you're going to keep the equations equal to mass times acceleration in that direction, and then just create your equations on the left-hand side. So now let's take this further, and I'll show you how to utilize these equations of motion. So what is system defined? Well, we need to identify what I want you to look at. And in this situation, to go forward, we're going to talk about this person running. The individual is running from left to right, okay? And the interaction happens with the system, the 1 foot and the ground. So I want to know the interaction of this runner with the ground during the running motion from left to right. And that's your task. Your task is to create a free body diagram. And so what you first do is go ahead and identify all the forces acting that you can identify. And you do that by doing vectors at the point of application in the line of direction that you see them. Okay, so it's very important, right? So as we go forward, I'll go ahead and, so you need to create the vectors and then give me what they are, right? So this one represents the force of air resistance, okay? Because the individual is running left to right, the air resistance is opposing that motion. And depending on what kind of day it is, sometimes if it's really windy and you have a wind that's coming from the back, then that may be actually aiding you in going forward. But for most purposes, you're always going to do this as resistance. Here you have the force of GRFY. Some people often put this as the frictional force. Okay. Here is your ground reaction force, or the normal force going directly up, and here is the body weight, or the force due to gravity, and that acts at the center of mass. So anytime you have a force of body weight or gravity, it should be at the center of mass of the system. Okay. each of the ground reaction forces occur at each contact point with the ground. So if I were to create my two equations of motion from this, what I would first do is, okay, which of these is in the vertical? I have, hopefully you can tell, you have 2 in the vertical, and I have 2 in the AP. So if I wanted to create the sum of the forces in the vertical equals mass times acceleration in the vertical, I would put on the left-hand side, I would have force of body weight, and I would have force GRF Z equals mass times acceleration in the Z. Now this is important. What you see is I just have 2 forces on the left-hand side. I haven't added any polarity or any sign, plus or minus, to those. So if I put over here on the left-hand side, this positive, positive, then I know that anything going up in the vertical is positive. So my GRF Z is positive, so I put a positive sign. That makes my body weight a negative. Okay, so I've summed these forces equal whatever it is there. If I know these forces, I can calculate what the motion's like. If I don't, this is perfect for what I'm looking for. I'm looking for a negative force of the body weight plus the force of ground reaction force in the Z is equal to the vertical motion of that system. Now, if I wanted to do the other one, which you always will do the 2, so I have the force of AP equals the mass times the motion of AP, right? The cause is the outcome. So I have force of air and the force of GRFY equals mass times acceleration AP. And in this situation, they are both negative forces, right? Because I have the positive in the right quadrant and they're both going left. So here you have a negative plus a negative equals mass times acceleration AP. So because of this situation, you can always assume, and we often call this position, there's a braking force. So the forces are slowing down this in the AP. So from this equation, you could simply say that whatever's happening is causing a reduction in the velocity in the horizontal. So this is how you use a free body diagram to create your equations of motion. And equations of motion, here's one equation of motion, here's 2 equations of motions. So when we talk about this system being defined, it's very important that you understand what the system is. Because often, and I use a cyclist in a cycle as my illustration of this because there are many different systems I can identify here. One is the bike and the rider as one system. So what I would do is this whole entire thing is one system and I want to know how it's interacting with the ground. So there's 2 points of interaction. The other way of doing this would be to say that I want to know the cyclist is one system and the bike is another system. So I want to know the interaction between the cyclist and the bike. So those are the 2 different ways I could approach the same exact scenario and have you identify the free body diagram of and the equations of motion of this picture. Commonly with this situation we would refer to the bike and the rider as a system because we want to see how that system is interacting with the ground, but oftentimes depending on the motion and what's happening is we would have the bike one object and the cyclist one object. So the system would be the interaction between the cyclist and the bike. And that would be 1, 2, 3, 4, 5, 6 possible points of intersection between them. And those are the normal forces, and that's where everything would come into play. Right, so if I said the bike and rider is a system, let me identify the force of the body weight, and I'm going to put it somewhere just here. I don't like that color, so I'm going to change the color. Right, so just the center of mass of the system. And so I'll have that going down, force of the body weight. If I want to create ground reaction force, and this important part of here is this ground reaction force. I'm going to put all the vertical in one color. is going up. And again, what's important for you to understand too, and I don't think I mentioned this before, is if I did the ground reaction force, really it would be coming like this. But we don't want to do that because I need to break it up into its vertical and horizontal components, right? So that's important. I want to already deconstruct it into its vertical and horizontal components because I need to use those in my equations of motion. I can't use a resultant vector in my equations of motion. Force of friction, and again, remember this is rolling friction. So the rolling tires are rolling this way. So my rolling friction are going to be two interacting at the surface going this way. And it's F of F, F of F. And going forward, I have air resistance, and that will be this direction. And we'll just put it acting here. And then if I go forward, propulsion, because the bike is going forward, and those are going to be going back here, propulsion, FP. And then I would take it further and have you create the equations of motion. And what I would do, instead of writing them completely out, you should be able to identify the number of forces in the sum of forces in the vertical, and that equals 3 forces, body weight, and the 2 ground reaction forces, and the sum of the forces in the AP, and you should be able to count them, 1, 2, 3, 4, and that's 5, both the frictional, both the propulsive, and then the force of air resistance. So hopefully you were able to create those, and then you would make each of those equal to the mass and acceleration within those, and that would be the AP and the vertical. So I hope that understands and explains to you how to create a free body diagram, and how important the system is in the process. And you use a free body diagram to create your equations of motion, which are going to describe that relationship between the forces applied and the outcome.